মাংসভাত স্পেশাল কিছু রাইস চিকেন ভালো।
So last class we have discussed about designing of a one-way slab, and we have take out the area of steel of area of reinforcement. The area of steel we have take out, and it is coming. AST is coming 540 mm². Next step is to find out the minimum area of steel. That should be 0.12. That is 0.12%, and finally we get it as 180 mm², which is actually coming less than 540. So hence the minimum area of steel of reinforcement that should be provided, that is 180, is up to the permissible limit. Next we have to take out the area of reinforcement with respect to the positive bending moment. Positive moment of reinforcement that is required for mu 18.35 kN/meter. Supporting that in the same equation, we will find the value of AST here, that is 461 mm². Again, it is more than 180 mm², hence it is okay. Next part is the distribution steel. So for distribution steel, we have to take out the area of reinforcement that is required, that is 180 mm². Now, if we take 8 mm bar, and the spacing of bar could be bar area of cross section into 1 meter width, that is 1000 mm by 180. That is the distribution steel. So from here we get the spacing required is 270. Can provide spacing less than this. So let us consider 270 mm center to center spacing of a 8 mm spread in the other direction for the distribution steel. So in the figure, as you can see, area of steel which is provided with respect to the mid span for the mid span portion, that is 461 mm². That is as per equation for the positive bending moment. So we can provide 10 mm dia bar with a spacing of 171, and at the midspan for the bending for the half of the bar that is bent up. So the remaining half will not be bent up. Bar that is provided at a distance of 320 mm center to center, and another steel that is available, that is the half 10 mm 320 mm center to center. That is the total available, that the steel that we have to distribute mm. So we have to provide required space. You can provide additional bar of 8 mm bar of center 100 at the support. So after the design has been done, finally we have to draw the sectional elevation of the and the elevation of the that and we must start with the support where we must show how much amount, how much quantity, what is the specification of the bar that is provided at the support, and how much quantity of bar is and we must also provide the enforcement that is provided for additional generation of tear, that is the extra steel that is required in the negative for the negative bending moment. That must also be shown. We must show the development length. So tension main provided. 50% of the bar 10 is provided center to center, and distribution bar 8 bar is provided at a distance of 270 center to center. And again, the same bar is bent up and it is taken upwards at the compression zone. That is 10 bar 320 center to center. And besides this, beside the bent up bar, we have to provide additional bar of 8 at a distance of 700 center to center. So both the bars are to be provided in the same direction. So this is how the fiber adjustment. Here. So that is already 30 minutes. So we will to view DV. So we will talk and for value of corresponding of PT, and from here we have to check the corresponding value of tau c, that is obtained from clause 40.2.1 of IS 456, where tau c is equal to Ks into tau c. The Ks value is obtained as 1.3 for the required depth, for the provided depth, and tau c value obtained as per the table 19 of IS 456, that is 0.46 after interpolation. So for the corresponding value of tau v obtained the PT to tau c, and finally tau c is obtained as 0.59 Newton per mm square, and tau c max we know is 0.5 into 2.8, that is 1.4. So we find out, finally we get that tau v should be less than tau c. So from here we can conclude that the shear reinforcement may not be provided. Next finally is your check for control of deflection. So that is obtained from the figure 4 of IS 456. So for the corresponding value of L by D max, that is KT into 0.26. So we will obtain the value of Fs for the corresponding value of PT, that is 0.46%. So Fs turns as 232 Newton per mm square. So multiplying the factor KT with 26 is 35.1. So L by D max comes out as 35.1, and L by D provided as per the question is 3920 by 120, that is 32.6. So we find out that L by D max is more than L by D provided. Hence, our design is okay. And it is successfully taking care of the deflection criteria. So this is all about the one-way slab design, one-way slab continuous one-way slab design. So let us start a new chapter, that is two-way slab. So the criteria for two-way slab, as you know, that those slabs which are called two-way slabs will have the criteria, the Ly by Lx ratio should be less than equal to 2. So the support condition of this type of slabs is that all the four edges will be supported, and in this type of slab the bending may occur in both the directions, means the bending may occur in the longer direction as well as in the shorter direction. So based on their support condition, they could be again classified into two types. One is your restrained slabs and another is your unrestrained slab. So in restrained slab, the two-way slab in which the corner will get lifted. So the corner will get lifted only when there is a provision for prevention of the lifting of the support, means at the corner, means there will be fixity at the support, and the fixity would be with the beams and wall, means they will be attached with the slab in such a way that the corner will be preventing from lifting up. So this is called restrained slab. So how these slabs are restrained? These are actually fixed. They are so not so for this, and this actual cracking of the corners. So that is why they are also called as slab with corners held down. So based on the fixity, the two-way slabs are again classified into by Indian standard due to their fixity. Uh, First case is when the slab is simply supported on four edges. So it will be simply supported on all the four edges on a beam by a beam, and the beam and the slab may be are cast monolithically, means at the same time they are casted. And another type of fixity is when the support on the edges by the four walls, the slab is supported on the edges by the four walls, and there are superstructure wall, and they are also above the slabs. So instead of beam here, the walls are carrying the load of the slab directly, and the fixity is also obtained because there is also wall that is present above the slabs. So this is how the fixity is obtained, and by this way the it resists the lifting of the corner edges of the slab. Beside this, there is another type of slab that is called unrestrained slab. So in this type of slab, as the name indicates, they do not provide any prevention against the lifting of the slab. So that is why they are called unrestrained slabs, and they are not held down at the corners. So these are the basic difference between the restrained slabs and unrestrained slabs. And all of you know what is two-way slab. So we define it by the maximum length by minimum length, length by breadth ratio should be less than or equal to 2. Means the direction, means the bending will occur in both the direction, may occur in both the direction, both the longer as well as shorter direction. Next, let us discuss about the IS code method for the design of two-way slab according to Annex D of IS 456/2000. So we have discussed about the restraint slabs. So from restraint slabs, we come across to see that the corners are held fixed and they prevent from lifting of the corners. So they may be designed as per the specification as shown below. So the first option is your maximum bending moment we have to calculate, and that maximum bending moment calculation of the slab is done by the per unit width of the slab by the equation that is mx is equal to alpha x into WL square. So as we have table previously, so W where W is the total load per unit area, alpha x and alpha y are the coefficients that we have discussed in the previous chapter, and Lx and Ly are the length of the shorter span and longer span respectively. So Ly is the longer span and Lx is the shorter span. And Mx and My are the moment of strips of unit width span, that is Lx and Ly respectively. So as you can see in the figure 1, we have the division of slab, and there are strips that are present at the edges and also middle. So this slabs are actually we're dividing it into three parts. One are the edge strips at the two end, and remaining portion is the middle strip. So based on their moment coefficient alpha x and alpha y, and the total load per unit area and the span, it depends. The value of moment, it is depending. So these slabs are actually divided into two portions, three portions rather. That is two edge strips and one middle strip. So as you can see in the figure, the middle strip is actually 3/4 of the longer span. That is 3/4 of the Ly. So you can also say that this is the 3/4 of the width of each edge strip, and the edge strip is actually 1/8 of the width, that is the 1/8 of the Ly. So this is the specification of the edge strip and the middle strip. So when we have to calculate the maximum moment, we have to use the formula, that is mx is equal to alpha x and to alpha x WL square হবে. And this is applicable for the middle strip, and if the condition is when there is no redistribution is occurring, we are not considering any redistribution of moment. So for this condition we will apply the formula as given in section 1.1. Now next, when we have to design the tension enforcement, the tension is provided at the midspan in the middle strip, and it shall be extended in the lower part of the slab, that is up to within 0.25 L. So this 0.25 L is for the continuous edge, and if it is discontinuous edge, then it is 0.15 L. Next section is 1.5, is about the continuous edge and mid strip, where the tension reinforcement may be provided in the upper part of the slab, and it should be provided at a distance of 0.15 L from the support, and it should be at least 50%, that is to be extended up to a distance of 0.3 L. So these are the specifications as per IS 456 that is to be maintained while designing. Next condition is 1.6, is your discontinuous edge. So at discontinuous, at the portion when where it is not, if there is no continuous edge, so there will be a generation of negative movement. So for this, there is a need of dependence on degree of fixity of the edges of the slab, but in general condition we only provide up to 50% of the tension reinforcement, and that is spanning up to 0.1 L, and that is sufficient to take the tension reinforcement, take the tension by providing the reinforcement equal to 50%, that is to be provided at the mid, that is extended up to the midspan up to 0.1 L. Next condition is your reinforcement in edge strip. So the condition here is that the edge should also comply with the minimum given requirements, and the requirement should be for torsion and also for the given upcoming three sections, that is 1.8, 1.9 and also 1.10. So let us see what are these sections. Section 1.1 tells that the torsional reinforcement shall be provided at any corner when the slab is simply supported on both edges meeting at the corner. So the torsional reinforcement that is provided at the corner of the slab, which when the slab is simply supported, so it should meet the both edges at the corner, and this torsional reinforcement shall consisting of both the top and bottom reinforcement. So both layers should be present. So each layer of the bars placed parallel to the sides of the slab, and it should be exceeding from the edges to a minimum distance of the 1/5 of the shorter span. So this reinforcement that is actually consisting of two layers, that is top and bottom reinforcement, which is actually placed parallel to each other, and the sides of the slab are also extended from the edges, and the distance up to which up to the side from the side it is extended is actually one considered as the 1/5 of the shorter span. Next condition is the area of the reinforcement in each of these four layers shall be 3/4 of the area required for the maximum midspan movement in the slab. So the area of the reinforcement that is provided, that is actually we are giving four layers, and this shall be 3/4 of the area required for the maximum midspan movement in the slab. This is section 1.8, which is about the torsional reinforcement that is to be provided at the corner of the slab for a simply separated condition when both edges are meeting at the corner. Now next condition is the torsional reinforcement that is to be provided, that is equal to half of to be considered as discussed in section 1.8, and it is to be provided at corner which are contained by the edges over only one, which is the slab is continuous. So when the slab is continuous, instead of the simply separated condition as discussed in 1.8, so in 1.9, the for the support condition continuous, the slab the torsional reinforcement which is provided for section 1.8, only half of the reinforcement is to be provided for the corner and when the corner contained by edges for the condition of continuous slab. Just a minute. Next portion is your section 1.10, where the torsional reinforcement is provided for the condition when the corner are contained by edges and when they are over both the slab when it is continuous. So when for this condition it will remain same. And for section 1.11, where the longer span by shorter span ratio is considered when it is greater than 2, then slab shall be designed for one-way slab for spanning 1. Next portion is for simply supported slab when they are unrestrained. So for this condition, for the simply supported condition when the slab is not provided with adequate torsional reinforcement and there is no provision for the corner to be registered from lifting. So for that condition, we have to same choose the previous equation only, that is mx is equal to a alpha x into w lx square, and my is equal to alpha y into w lx square. So mx and my, moment of movements for the shorter span and long span x and ly. So same equation used the specific error. And find the maximum movements at the shorter span and longer span. The next condition is that at least 50% of this tension reinforcement is to be provided at the mid span, and this should extend up to the supports, and the remaining 50% it should be extended up to within 0.1 lx or 0.1 of the support period. The that we know criteria also. So we have considered this order thirty-five into 0.8, that is 28 for Fe415 deformed bars. That it is 40. So 40, that is equal to 40, that is for mild steel. And if you consider 40 into 0.8 for mild steel, that's 32 for Fe415 steel. So this is the criteria. So as I have discussed, the effective span is to be calculated. The distance and plus effective depth is to be calculated, and we take the least value that is coming 161 meter. So the LX and LY value we have obtained from here 4.161 meter and LY is 5.161 meter. And considering the effective depth as considering overall depth is 180 mm and effective depth can be considered by subtracting the clear cover considering bar design load W. So we know that concrete. So from here we get the self weight of the slab. 180 mm is the overall depth that is considered. 4.5 kilonewton per meter. Kilonewton per live load. Kilonewton per meter. Total load comes as the factor 1.5 get 14.25 kilonewton per meter. So as per question, it is asked to consider at this the at all the four corners the slab is held down, and so we will consider the case 9 of and we will consider the table 1 for our calculation. So from the previous table we can obtain the value of Ly by Lx, and from interpolation we can obtain the corresponding value of alpha x and alpha y for Ly by Lx ratio 1.25, and finally we can obtain the mux value from by equating all the values. So finally we get the value of alpha ux is equal to 18.5 kilonewton meter, or we can convert it into Newton millimeter. Next, similarly, can calculate the value of mu y, that is mu y 0.056, that is the value of alpha y into w into Lx square. So here we can obtain the value of mu x and mu y like this. Next is the maximum shear force calculation, that is by so 4.161 by required that we have the value of IU value for so common, hence next is the design of main reinforcement. So along the shorter span, if we consider in the x direction, for considering the by considering the middle strip, we will get the width of the middle strip, that is equal to how much 3/4 of Ly. So 3/4 of Ly is 3/4 into 5.16, that is 3.9 meter, and D given is 161 mm. So from here we know that we have to find the value of AST. So we can obtain it by the M is 0 by the solving the quadratic equation, and it is coming 332.5 mm square. So we can use 8 mm bar to distribute the reinforcement area. So 50.3 mm square is the area of reinforcement of each bar into width 1 meter, that is 1000 mm by AST given 332. So from here we obtained it is 151. So suppose 150 mm can be the thing that as per requirement of IS code, that be less than 3D or 100 mm. Okay, that's all for today. All of you write your name